My name is Farah Syafiqah Bakar and my mentor number is BWD21903. Today I like to discuss a fascinating topic in the realm of thermodynamics, the freezing curve. Understanding the freezing curve is essential for grasping how substances transition from liquid to solid, and it has a numerous practical application in the field ranging from meteorology to material science. So, what is a freezing curve? A freezing curve is a graph that represents how the temperature of a substance changes as it transitions from a liquid to a solid state during the freezing process. It demonstrates the connection between the product temperature and the amount of time needed for it to fully freeze. The food product goes through a series of temperature fluctuation during the freezing process as it moves from its starting temperature to the required frozen state. The freezing curve offers information on the rate of heat transfer and the amount of time needed for a complete freezing, which aid in understanding and optimizing the freezing process. It also helps to study the phase change behaviors of various substances and understanding thermal properties. Supercooling is one of the phenomena happening in the freezing curve. Supercooling occurs when a liquid is cooled below its normal freezing point without becoming solid. It requires a pure substances and a minimal disturbances. As example, water can be supercooled below 0 degrees Celsius without freezing if the conditions are right. Next, we move to the freezing curve. At point AB, the food is cooled to the below freezing point. At the point S, the water remains liquid although the temperature is below the freezing point. This phenomenon is known as supercooling and may be as much as 10 degrees Celsius below freezing point. At point BC, the temperature rises rapidly to the freezing point as ice crystals begin to form. A later heat of crystallization is released. At point CD, heat is removed at the same rate as before, and later heat is also being removed as ice forms and the temperature therefore remains almost constant. The freezing point is gradually depressed by the increase in solute concentration in the unfrozen liquor and the temperature falls slightly. At point GE, one of the solute becomes supersaturated and crystallizes out. The later heat of crystallization is released and the temperature rises to the atheistic temperature for that solute. At point EF, crystallization of water and solute continue. The total time taken is determined by the rate at which heat is removed. Next, there are three components of freezing curve: cooling phase, plateau phase, and solidification phase. Cooling phase is when the temperature of the liquid decreases as it is cooled. This part of the curve shows a continuous drop in the temperature until the liquid reaches its freezing point. Plateau phase is once the liquid reaches its freezing point, the temperature stabilizes and remains constant for a period of time. Lastly, solidification phase is after the phase change is complete. The temperature of the solid substance continues to drop as it is further cooled. This part of the curve again shows a decrease in temperature. The freezing curve is more than just a theoretical concept. It has a significance in food preservation, which enhances technique for freezing and storing food to maintain quality, in cryogenics, which is critical in the study of material at really low temperature, and in meteorology, in helping to predict frost and understanding ice formation process.